Good day, ladies and gentlemen. We are the Group 10 and presenters for today. For proper introduction, I'm Mark Jason B. Janala along with my group mates, Renzo, Caldito, and Julianne Marie Arias. So let's start with this beautiful quote. This quote is written by James Joseph Sylvester, an English mathematician. He said, "Mathematics is the music of reason." Wow. Here's the context of our presentation: the introduction to linear independence of function and the Wronskian. For the linear independence of function, they are said to be linear independent if and only if they are not linearly independent. In other words, when the vectors are linearly independent, their only linear combination that results in a zero vector has all the coefficients equal to 0. And it should be clear that if the functions of a set are linearly independent, at least one of them is a linear combination of the other. If they are linearly independent, none of them is a linear combination of the others. And to determine the linear independence of function, we use the Wronskian, and it will be tackled by Caldito.
The Wronskian is a determining factor in mathematics introduced by Thomas More and named by Joseph Owen Wronski. In the analysis of differential equations, it is used where a sequence of solutions may often illustrate linear independence. The Wronskian of two differentiable functions of f and g is written like this. The Wronskian of f of g is equal to the product of the functions of f multiplied by the derivative of functions of g minus the product of function of g and the derivative of function of f. More generally, for n real or complex valued functions f sub 1 to f sub n, which are n minus 1 times the differentiable on interval 1, the Wronskian f sub 1 to f sub n as a function 1 is defined by this. So, in other words, it is the determinant of the matrix that is built by putting the first row functions, the first derivative of each function, and the nth derivative, thus making a quadratic matrix. In the case of a linear differential equation solution, Wronskian can expressly be found using the identity of Bell even though the five functions are not explicitly known. And let's try this example. So we're given with two functions two functions. F of x is equals to x and g of x is equals to x cubed. Now let's determine whether the two functions are linearly dependent or independent. So now first let's make our Wronskian, and the first step was creating a column and rows, and on the first row that should be our main functions f of x and g of x, and on the second row that should be their derivatives, and it will look like this. The f of x is equals to x and g of x is equals to x cubed. Therefore, their derivative should be 1 and 3x squared. Now, cross multiply and subtract, seeing if it equals to 0. And when we cross multiply, x multiplied or x times 3x squared and 1 times x cubed. X times 3x squared will give us 3x cubed, while 1 times x cubed will just give us x cubed. And since these cross multiplied products were being subtracted from each other, Wronskian is equals to 3x cubed minus x cubed, it will give us a final value of 2x cubed, which is as we can see, does not equal to 0. And as we mentioned before, when the run scale is not equal to 0, then two functions are independent. But if it equals to 0, then functions are dependent each other. And here's another example of how run scale should be solved.
Here is another example on how to determine whether the functions are linearly independent or independent. So here, f of x equals to e raised to the x, and g of x is equals to e raised to 2x, and h of x is equals to e raised to 3x. So the first step is to make our 3x3 Wronskian. So here we put the f of x and g of x and h of x, which is the e raised to the x and e raised to the 2x and e raised to the 3x. So we get their first prime and double prime. So each of that, we put it downwards. Okay, so next we need to add 2 more columns. Remember, there are just the first 2 repeated. So we put the first 2 aside and we multiply it. Okay? Now, we can cross multiply and subtract to save space. We will do this 3 at a time. Here are the first 3 terms. So, we cross multiply and subtract. So, we get e raised to the x times 2e raised to the 2x times 9e raised to the 3x plus e raised to the 2x times 3e raised to the 3x times ex plus e raised to the 3x plus ex times 4e raised to the 2x. So we get, if we solve it, we can get 25e raised to the 6x. Now remember, that was only the first half. Now, starting from the bottom, we need to find the next 3 terms and subtract them from the first. Now we can get 25e raised to the 6x minus, subtract them, minus e to the x times 2e raised to the 2x times e raised to the 3x plus 4e raised to the 2x and times 3e raised to the 3x times e raised to the x plus 9e raised to the 3x times e raised to the x times e raised to the 2x. So if we solve this, we can get 25e raised to the 6x minus 23e raised to the 6x. Now we can get 2e raised to the 6x. So it is not equals to 0. So the Wronskian does not equal to 0, so that the functions are linearly independent. So that's all. Thank you for listening. This is our report for linear independence of functions.